Thank you. Okay, so thank you very much, you, for the kind invitation, and also thank you all for coming. It's a great pleasure to be able to share some of my research ideas and some general kind of ideas which I think is interesting from data science perspective with all of you. So I would like to keep my talk primarily, I'll try to build it up from keeping in mind a pretty applied focus, and then gradually I would expand the scope of this talk to some interesting theoretical issues on which I've been working. So let me start with a little bit of a discussion on randomization-based perspectives of experimental design. And I'm sure most of the people in the audience are familiar with the concept of experimental design and randomized experiments, and especially in view of a few Nobel Awards to people working in randomized experiments in 2019, and then recently this year, Guido Imbens received an award for working on causal inference, which is again very closely tied to the notion of randomized inference. So over the past couple of years, there has been quite a recent search in this on this topic. However, this randomization-based perspective of experimental design has served as a foundation of experimental design since a very long time. And it was based on seminal work of two stalwarts, Neyman in 1923, Fisher in 1925. And it had a very close connection to a subject in statistics, which was called survey sampling. However, quite unfortunately, and also interestingly, this randomization-based perspective seemed to die down in the later half of the 20th century. And one of the plausible reasons which can be attributed to this could be the lack of computational resources, because as we move along our talk, we shall see that there are elements of this randomization perspective, and specifically associated with the Fisher randomization test, which involve heavy computing. So if so it's quite understandable that towards the middle of the 20th century, there clearly was not enough scope of doing these kind of analysis. But now we can really harness the power of modern computing, and we shall see how these notions can contribute to modern data science in a big way. So let me start with a very simple motivating example, and a randomized experiment which comes from the field of education. So the idea is to examine the impact of a treatment on the performance of school. So the treatment here is what happens if the teachers of a high school are given a performance-based bonus. Okay, so this kind of experiments are conducted by Department of Education of, let's say, New York State or different states in the United States. So let us start with a very simple format of this experiment, where we have only 12 schools as the experimental units. Compare that they would be a performance score on a scale of 1 to 100. Can you hear me, you?
Yeah, so you have a broken moment about 30 seconds also. I heard your last sentence about the performance score 1 to 100.
Okay, I'm sorry, I'm not sure why this is happening, but yeah, please, can you just, yeah, I'll just check once again if this happens, and maybe switch to a different connection, which may be a little more, okay. So sorry about that. We are just trying to examine the impact of a treatment, which is a performance bonus on schools. And there are 12 schools, which are our experimental units. So the idea is to examine whether a treatment which is implementing a performance bonus has an impact on the performance of the schools. So what we'll do is we'll just review some very basic designs for this experiment and the popular analysis methods. And then we shall see that how these kind of very common or well-known designs can be replaced by a randomization-based analysis. Okay, so let us first think about a very simple design, which is a completely randomized design. CRD is an acronym which is often used for this design. So let's assume that we have 12 experimental units, and as in a typical randomized experiment, we would assign 6 of these units to treatment and 6 of these units to control. And as we mentioned in the previous slide, the response would be a performance score on a scale of 1 to 100. Okay, so suppose this is the data which we obtain. So these are the 12 units or the 12 schools. And out of these 12 schools, we have 6 schools who were assigned to the treatment and 6 schools who were assigned to the control. And this assignment is denoted by this assignment variable T, which is 1 if that unit receives the treatment and 0 if not. And these are the scores. Okay. So how do we analyze the data? This is something which we all are familiar with, right, in our basic statistical methods. So you would like to test the hypothesis that the averages of the treated and the control groups are equal. And for that, this is what we would do in most cases. We would use a 2-sample t-test, let's say, in a package like R. And we would like to compare the observed averages of the 2 populations who receive treatment and control. And then we would like to draw an inference based on the p-value of the test, right? So this is something which we are pretty familiar with, and it typically constitutes the first chapter of any common experimental design book. Okay, so however, let's move on to a slightly more complicated scenario where our experimental units still are 12 schools and we have a very similar setting, but now let us say that some covariate information is available, okay? And that covariate is the number of students of these schools. So, so let's say that there is an assumption that the performance of the school is strongly dependent on the total number of students. And this number of students is a covariate. So the question is, how do we modify the design? Should we modify the design, right? Because it is possible that once we assign 6 units at random to the treatment group and 6 at random to the control group, in that case, these 2 groups could be heavily imbalanced in terms of the number of students, right? So we would think that completely randomizing these 12 units to the 2 states of treatment and control may not be a very good idea. So instead, what we do is we think about a blocking approach, right? So we create 2 blocks. We divide the population of schools with less than 1,000 students, let us say, as represented by the blue cells. So these schools have enrollments less than 1,000. So this is one block. And then the schools indicated in yellow are the schools which have enrollments above 1,000, right? So they represent another block. So these are the yellow cells. And then within each cell, within block 1 and block 2, within each block, we try to make sure that we use a completely randomized assignment so that 3 units within each block receive treatment and 3 receive control, right? So this is what we refer to as randomized block design, and then accordingly we look at the data, right? So this is just one step ahead of completely randomized design in the sense that we try to create a scheme so that the treatment effect is not confounded with the effect of a covariate about which we have prior information, right? And we use that to form a block. So how do we analyze the data from this? And in most experimental design books or linear models book, one would use, let's say, an analysis of variance to do that. So you would use a 2-way analysis of variance in this case, where factor, this B, this blocking factor is one of the factors, and then the treatment is another factor. And then you would just sort of use y-obs, the observed data, the response, and find out its analysis of variance decomposition with respect to these two factors, right? And then we would look at the factor treatment and look at this p-value. And if this p-value is very small, we would possibly conclude that the treatment has any effect, right? So this, in most experimental design books, is again, let's say chapter 2, if completely randomized design is chapter 1, randomized block design is chapter 2, right? So then what would be chapter 3 in a randomized design book? Suppose we have the same setup, but unlike the previous case, where we believe that the performance of a school is dependent on the enrollment, here we believe that the performance is very strongly dependent on the total number of students, okay? So, for example, even a difference of 200, 300 students can make a major difference. So what do we do in this case? We would like to create more blocks, right? More strata, and then make the comparison within these blocks, which would be more similar to each other with respect to that covariate, right? So in the extreme case, what we can do is we can pair the 12 schools, just like we do in the case of identical twins, right? So we take a school and find its identical twin in terms of the enrollment. And within each of these pairs, we have one treated and one control, and then we compare their performances, right? So this is an extreme case of blocking, which we refer to as a matched pair, right? So this is how the design is conducted. So basically, when you look at the units, you try to match each school with another school, right? With the closest possible enrollment, right? And then there can be various matching algorithms by virtue of which you can divide these 12 units into 6 pairs, right? So like this yellow is a pair, this blue is a pair, right? So they have very similar enrollments. And within each pair, now I toss a coin and assign the treatment or the control to one of these two units, right? So this is again also a randomized block design. The only difference being the definition of the blocks is much more stringent, and we have the maximum possible number of blocks in this scenario. So we have this data. And how do we analyze it? One simple way is to use a paired t-test instead of a 2-sample t-test, but the other possible way is also to use an analysis of variance in exactly the same way as we do for a randomized block design. So in this case, the only difference would be that the degrees of freedom associated with the blocks will be much higher because we now have 6 blocks, and everything else would remain the same. We could do the ANOVA decomposition, and then we could calculate the F value and make a decision, right? So till this point of time, we have just basically discussed a practical example. And how would that practical example be mapped, let's say, on the first 3 chapters of a very basic experimental design book, and how we would do the analysis, right? So as we kind of see, the steps in this model-based analysis can be actually listed down as bullet points. We are essentially looking at a hypothesis testing framework where we are testing equality of 2 treatment means. In all of these cases, we have assumed a linear model, which implicitly assumes that there are residuals which are normally distributed. Then we found a suitable test statistic like the 2-sample t or the paired t or the F in the ANOVA setting. And then we calculated the distribution of the test statistic under the null hypothesis. So the t statistic is a t, and that follows from the normality of the residuals, right? In an ANOVA setup, the F is indeed an F distribution under the null, also follows from that normality. And then, of course, we reject the null if the observed value of the test statistic is very unusual or extreme, which means when we actually calculate the p-value, it is very small, right? So these are basically the steps which you can think of as common steps in this model-based analysis. And the model in this case differs because there is a different design associated with each model, but there are similarities as well in the sense everything is under the purview of a linear model, the residuals are assumed to be normal, and everything else follows from that normality, right? So now suppose we want to replace this model-based analysis with a model-free analysis, where this model-free analysis is driven by the design, is driven by the randomization scheme which we adopt, okay? So let's see what changes if we move from the earlier regime to this regime, okay? So we are still considering a hypothesis testing framework, but now, as we shall see, we will consider a slightly more stronger hypothesis. So in the earlier case, we were trying to compare a hypothesis of equality of the means of two groups. Okay. Now we will think of a stronger hypothesis, which is often referred to as the strong null or the sharp null, which says that there is no treatment effect on any unit. So equality of treatment effect for each unit, each of the 12 units. Okay. So the linear model assumption of normality of residuals will be replaced with, we will not consider any model. There would be no normality assumption. And instead of finding a suitable test statistic, we can start with any reasonable test statistic. What does reasonable mean? Some statistic which measures the difference between the treated and the control group in terms of the response. That could be difference of the means, that could be a standardized difference of means, that could be a difference of medians. And then we would find the distribution of the test statistic under the null hypothesis. Unlike in the model-based approach, which is obtained through the model, we would obtain this through the randomization distribution. Here is where that design is going to play a very crucial role. Okay? And then, of course, the decision rule is going to remain the same. Okay, so let's see how the analysis now changes, or how we perform the analysis if we consider this method of analysis. So in the first example, when we were thinking about the completely randomized treatment, we could consider a reasonable test statistic as the absolute difference of means in the two treatment groups, right? So let's say this is the treated group, this is the control group, and the absolute difference of these two can be considered as the test statistic, and this is the observed value of the test statistic from our data. Okay, so now we would like to see whether this observed value is unusual with respect to the randomization distribution of the test statistic, which is the absolute difference in this case. So how do we find statistic? Okay. Now what we do is we would like to I'm just trying to check whether the
another 30 seconds.
Oh, can you give me just 2 seconds? I'm trying to switch to an internet connection, which I think will be a little more stable. I'm really sorry about this. I don't know what's happening. Okay. Okay, so what I think where we were just thinking about replacing the model-based analysis with this model-free randomization-based analysis, where we still have these 12 units, and these are the data. So the first row in this represents the actual or observed binary vector of the treatment assignment, which we actually obtained from our design. And this is the observed value of the test statistic, which is the absolute difference of the two treatment groups. Okay. So now the next step is to find the randomization distribution of this test statistic. So how do we derive that randomization distribution of the test statistic? We will just kind of flip this vector of treatment assignments to generate all possible binary vectors which can arise as a consequence of the same randomization scheme, right? So basically our randomization scheme is a completely randomized scheme, right? So what that means is we have a pre-assigned 6 and 6 units assigned to the treated under control. So there can be 924 possible permutations of this vector 0 and 1 as we see in each of these cases, right? So if we assume that the data would remain the same, the data would not change, right? And what is that implicitly indicating? So what this means, if this particular unit received the treatment, or if this unit received the control, this observation would not have changed, which means there is no effect of treatment on this particular unit. And that is true for all of the units, right? So I can replace the data for a unit, or the observed data for a unit, right? So I can basically use the observed data for a unit in both of the scenarios, irrespective of whether that unit receives a treatment or a control, right? So all I change is basically the assignment vector, and then I generate the absolute difference of means in the same way. And then I have 924 possibilities over here. And that gives me the distribution of the test statistic under the null. And once again, so the null here is there is no treatment effect on any unit, which is actually allowing me to generate this distribution through this generation of these 924 possible vectors, right? So then I can create a histogram of these 924 possible units, these 924 possible values. And this is my observed value, from which I can calculate a p-value, which is something like 0.04. And this is small, so I can conclude that I probably have some evidence, strong evidence against the null hypothesis. Okay? So this is the basic mechanism. So if we understand this mechanism, then we can use exactly the same approach to conduct hypothesis tests for any design. As long as I know the randomized mechanism, which is used to generate the data, I can make use of that randomization scheme to generate the distribution of my test statistic. So let us say the second example was a block design, where you would remember that we had divided these 12 schools into 2 blocks of size 6 each based on the number of enrollments. The yellow block was schools with smaller enrollments. The blue block was schools with larger enrollments. So the first row, once again, is the actual assignment, where within this block I had 3 ones and 3 zeros. Within this block I had 3 ones and 3 zeros, and this was my observed value of the test statistic, which is the same as before, right? So now I generate this data, this binary vector of assignment just by replicating or drawing from that same design, which is selecting 3 and 3 treated and controlled within each of these blocks. So now the total number of possible randomization would be much less, and that is because of this blocking restriction imposed. So I would have 20 possibilities here and 20 possibilities here. So in all, I would have 400 possible permutations of this vector. And then I would similarly calculate the observed difference of the means. And then I could generate the randomization distribution of the test statistic exactly in the same way. And I can calculate my p-value and make a decision, right? So once again, if you see the way we are proceeding here, right, is we are considering any test statistic which is reasonable, calculating its observed value, and then we are generating the randomization distribution of that test statistic under the null hypothesis, or more specifically under the short null hypothesis. So we are just drawing from the distribution of the treatment assignment vector, and each draw gives us a possible value of that test statistic, and then we calculate the p-value using that distribution, right? And let's look at the third possibility now. So this is the case where we use the matched pair design. So we considered these 12 schools and we paired them up into groups of 2 based on their closeness on the X scale, which is the enrollment scale. So within each of these 6 blocks, we simply tossed a coin and assigned one of these units to the treatment and one of these units to the control, right? So this was again, let's say our observed vector, and this was the observed test statistic, which again remains the same. So in this case, we just have 2 to the power 64 possibilities. And these are the absolute difference of means when we permute this data vector based on that design, right? So, and then this is a randomization distribution of the test statistic. And once again, we can come up with a very similar distribution and calculate the p-value. The only thing which we observe is the number of permutations are drastically going down as we are moving from a completely randomized design with a very tight block design, which is a matched pair design. So from 924, we went to 64 possible combinations. But at the same time, we are trying to protect our design from the effect of this covariate, which is the enrollment in the schools, right? So this is where the trade-off is being done, right? So
Tirthankar, can I ask you a quick question here?
Absolutely, yes, yes.
So you see the p-value is getting bigger, right?
Yes, so this again, I think there is obviously no guarantee that this will happen, but of course we expect that as you block, right, you are trying to draw more precise inference. So that comparison between the two groups would be more tighter, right? So if you have very similar groups, right, and if you have a sufficiently large sample size, then you would obviously expect that as you impose more restriction on your design, you are trying to balance the two treated groups more, right? So that p-value with kind of pretty large sample sizes should get kind of smaller as you impose more restrictions, right? So although with this kind of a sample size, it is not obvious, because what might happen is in this case, for example, the smallest possible p-value which you can get from this kind of a test would be just 1/64, right? Whereas in a completely randomized design, the smallest possible p-value would be 1/924. Right? But on the other hand, you are making your comparison more precise, right? So the idea is when we conduct a randomized experiment, the idea is to make a fair comparison, right? By comparing two balanced groups. So these groups, by virtue of our complete randomization, should be balanced, but then they are balanced only in expectation on an average. So in an individual design, in an individual experiment, your groups can actually be very imbalanced, right? So that is the essential idea of blocking. So you are bringing in more restrictions so that the two groups are more balanced, right? And then in this extreme case, you are trying to make sure that your two groups are, again, even more balanced, right? So that increases the precision of comparison, right? And that is one of the reasons why if you have sufficiently large sample size, and if this covariate is indeed having an impact on your response, then you obviously should get a more precise inference. Okay.
Okay, thank you.
Any other questions at this stage, or is the kind of idea of doing a randomized test, randomization based test, and its comparison to a model-based design clear? Please feel free to interrupt me if there are any questions at any stage. So basically, when we think of a design, right, we are thinking about the allowable randomizations to prevent confounding from covariates. So even before the completely randomized designs, we could have used a Bernoulli design. That is, for each of these 12 schools, we could have tossed a coin, and we could have independently, and then we could have decided whether that school would be assigned to a treatment or a control, right? So in that case, we would have 2 to the power 12, a larger number of possibilities. But that wouldn't be a very good design, because that might lead to a situation where all schools are either assigned to the treatment or all schools are assigned to the control, although that will happen with a very small probability. In the completely randomized design, we see that we had 924 randomizations, which are allowable, right? In the randomized block design with 2 blocks, there are 400 randomizations which are allowable, right? In the match pair design, there are 64 randomizations which are allowable, okay? So as we are kind of moving up the scale or tightening the comparison and making sure that we are comparing to more and more and more balanced groups by blocking on something which can create a confounding effect, we are kind of slowly improving the balance, but the total number of randomizations is going down. We are analyzing this experiment using a randomization test. So the nice thing is this works for any test statistic, right? So any reasonable test statistic works, whether it's the absolute value of the difference of the means, or whether it's the difference of the medians, or whether it is the difference on a log scale. Everything is going to work. Everything is going to give us a valid test, right? Because we are going to calculate the observed value of the test statistic. We are going to generate a distribution of the test statistic using repeated assignments, but that repeated assignments would be generated using all the allowable randomizations only, right? And then we would determine if the observed value is unusual. So, so this is, in a nutshell, the idea of a randomization test. So where does this take us? And I would like to try to give some insights as to why this could be very useful in modern day scenario where we do have kind of different kinds of experimental scenarios where we have large number of covariates and things like that. So this was a long time ago when one of my former colleagues at Harvard, Sam Coe, we were having a conversation about experimental design, and he said he didn't like the topic of experimental design very much because chapter 1 was like completely randomized design with 2 suffixes. Chapter 3 was randomized block design with 3 suffixes. And then chapter 4 was Latin square design with 4 suffixes. So apparently kind of as he moved along these chapters, so the number of suffixes and the complexity of the models was increasing. And at some point of time, it became a little unintuitive, right? So this is, I think, where this randomization based approach can create a very intuitive understanding of the relationship between the design and the analysis. And that's what Fisher had said, analyze as you randomize. But more than that, we don't necessarily have to stick to these standard designs and have chapter 1 as CRD, chapter 2 as RBD, or chapter 3 as matched pair and things like that. So basically the idea is how balanced do we want our treated and control groups to be, right? So the completely randomized design is a starting point because as you mentioned, and we were having that discussion a little earlier on, that the idea is to create 2 groups which are balanced, right? So that's a fair comparison. But completely randomized design only guarantees that that balance is on expectation, right? But then you could be unlucky and you could get an assignment which eventually results in a heavily imbalanced treated and control group, right? So we try to tighten the screws using the confounding covariates which we have in our data, right? So we try to construct randomized block designs, or we try to construct matched pairs. But we don't necessarily have to stick to standard designs. And indeed, this technique of blocking tends to get more unintuitive if we have a large number of covariates, which happens in modern experimental scenarios, clinical trials, where you have a large number of covariates associated with each patient before, for example, you're doing a vaccine trial or things like that. So the basic idea is, what do I want, right? What does a domain a scientist really want? How balanced does he or she want the 2 groups to be, right? And based on that, I can create a definition of my allowable balance, right? So I just need to come up with a balance measure. And then I need to see, like, what would be the allowable set of randomizations which would help me achieve that balance. I should declare it a priori. And then the advantage is I can immediately conduct a randomization test because the principle is the same. I generate all these treatment assignment vectors only using the allowable variation, right? So everything works exactly in the same way. So we could actually be a lot more flexible when it comes to designing our experiments. So let me just try to explain a little more what this means in the context of this example, and then we can go to a higher dimensional case. So let us say, in this case, basically, why are we worried with a completely randomized design? Because we believe that the enrollments can be a confounding factor, right? So X is the number of enrollments. And this is our completely randomized design, right? So it happens that in this particular case, when I'm comparing the balance, which can be defined as the absolute difference in the enrollment between the 2 groups, which is a logical way of visualizing how balanced the 2 groups are. So that difference, this is like something like X0 bar, which is the average enrollment in the control group, minus X1 bar, which is the average enrollment in the treated group, right? So that is 352 or something like that. In the randomized block design, in this particular example, it comes down to about 23. In the matched pair design, it is even less. And this is intuitive, right? Because you are trying to put these units closer together. And that's the basic idea of blocking, right? So if we just think of all possible scenarios which these 3 designs would have generated, right? For the completely randomized design, you could have obtained a largest difference of means of enrollments of the 2 groups somewhere in the proximity of 400. In the randomized block design with 2 blocks, this distribution would have shrunk with a maximum of around 200. And for the matched pair design, this would have been even smaller if we consider all 64 possibilities. The worst possible scenario would be something like 100, right? So, so let's just think about this for a second. So if we now think about basically the idea of designing an experiment is to create two groups where we want this average difference between the number of enrolled students should be less than something, a threshold, right? So then we don't have to stick to one of these three designs, but we can create something in between. We can create something in between, and we can come up with a design which is basically our own design and which is closely related to the practical scenario which we are investigating, right? So, for example, we can declare all assignment vectors that yield balance measures not exceeding 300 as acceptable, right? So this design would be stricter than a completely randomized design, but it would be less strict than a randomized block design with 2 blocks. Once again, we could declare all assignment vectors that yield balance measures not exceeding 150 as acceptable, right? This would be stricter than randomized block design, but this would be less strict than matched pair design, right? And the nice thing is a randomization test for these two designs can be performed in exactly the same manner as before, okay? So we only need to make sure that an allowable randomization is defined before we design the experiment, and the same rule is followed using analysis while generating the randomization distribution of the statistic, okay? So this is basically the only idea which goes into developing these kind of designs. So this is why it can be very useful in modern experiments where typically we would have a lot of covariate information about each experimental units. So in the school experiment, in reality, we did have almost 50 to 60 covariates associated with each school, which included previous year's performance score, total number of students, race variables, right? Proportion of white, black, Asian, Native American, proportion of female students, enrollment rate, poverty rate in neighborhood, and so on and so forth. So blocking is pretty unintuitive in this kind of a scenario. So let's see how this entire idea would work in a two-dimensional covariate scenario, right? So let's say in this figure, we are looking at this balance measure. So this is the difference between the average of covariate 1 between the treated and control groups, right? This is the difference of the averages of covariate 2 between the treated and control groups. So a best perfectly balanced design or perfectly balanced assignment would be one where both of these are exactly at the center. That means the treated and the control groups are exactly the same with respect to both covariates, right? So a point on this scale, on this two-dimensional graph would indicate one possible assignment, right? So this means that this is where you have the difference of the first covariate between the two groups, and this is the difference of the second covariate between the treated and control groups. So each of these points would represent one assignment, right? So there could be several assignments, and then you could decide that there is a certain region which would be considered as an acceptable region, right? So you may actually create something like an ellipsoidal region which you would declare as the region of acceptance. So as long as your randomization falls within this, right, then that randomization would be acceptable. If it falls outside this, that would not be acceptable. As long as you define this a priori, right, everything is fine. You can immediately use this acceptance rejection type of draw to generate your data, to conduct your design experiment. And then you can use the same mechanism to draw from this distribution, right, which would just be something like an acceptance rejection sampling. You draw from this distribution as long as it satisfies the criterion, and each such draw would help you generate the distribution of the test statistic, right? So one criterion which has been used quite abundantly in recent times is the well-known Mahalanobis distance, which is multivariate distance between groups of two mean vectors. And you could use an acceptance criterion, which is something like this: M is smaller than or equal to threshold A, where A is a predetermined constant. So this predetermined constant can be obtained based on the randomization distribution of M, right? Which again, for large samples turns out to be something like chi-square. And so the trade-off is between throwing away randomization and balancing groups, right? So that here is the trade-off. How strict you would like to have your groups balanced, how closely you would like to have your groups balanced, right? And of course, that would have an impact, like you have to throw away more randomizations, right? But everything else works exactly in the same way. So this is what would eventually happen is if you used a completely randomized design, this would, let's say, be the distribution of the difference of the averages between the treated and control groups. And this would be where you would have a shrinkage after you would actually impose that threshold of this Mahalanobis distance smaller than A. So, okay, so this is the general idea, but all the analysis would be exactly the same. That is, we would just consider this test statistic, we would just consider its randomization distribution, and that distribution now would be generated with all acceptable randomizations, the definition of which is those randomizations which satisfy this criterion of m less than equal to A. Okay. So any questions at this stage? Is this clear? The concept of okay. How much time do I have you?
The seminar ends at 2:40, but you know, consider the disruptions, the connection problem. You know, just keep going.
Okay, maybe we'll just go over to one interesting example. So before I come back to this, let me just think about how this entire idea can be expanded to, let's say, factorial designs, right? So this actual school experiment did involve 224 schools in all, and there were 5 new interventions. So the school performance bonus was just one of these. So the response was a cumulative score, as we mentioned. So this was in reality a 2 to the power 5 factorial experiment with 5 factors each at 2 levels, right? So this quality review was something like whether you would want a team of experts to come in between and conduct a review for that particular school, whether that would improve the performance of the school. Okay, so in a factorial experiment scenario where we have 50 covariates, right? Now, how would you visualize this problem and how would you analyze this problem? So we would like to think about how to balance these 50 covariates, right, over the treatment groups. But when we define treatment groups, what do we mean? Now, we have 5 main effects here, right? So 5 main effects means that you would have 5 different possible groupings of zeros and ones, okay? Then we would have 2-factor interactions, which mean we would have 10 possible 2-factor interactions, and each 2-factor interaction is also represented by a binary vector of zeros and ones, which means we would require some sort of balance over these 0 and 1s, right? And then, of course, we could have 3, 4, 5-factor interactions. So when we are thinking about generalizing this to a factorial experiment scenario, we are thinking of several binary columns over which we want to achieve balance over the zeros and ones, right? So here, once again, we may actually use something like the effect hierarchy principle, which says that we are most interested in providing protection against our main effects, followed by 2-factor interactions and so on and so forth, right? So we can use the same idea of creating a criterion based on the Mahalanobis distance, but then we have different criteria for main effects, we have different criteria for 2-factor interactions, and different criteria for 3 and higher order interactions. So when we actually implemented this design, we tried to protect these main effects to the maximum possible extent. So we were very stringent with the criteria for the Mahalanobis distance for main effects. So we were able to reduce the variance of the 2 treatment groups by almost about 40% for main effects. And we aimed at reducing the variance for the 2-factor interactions by 20%. And we did not aim at reducing variance of 3-factor interactions or higher order interactions. So, so this was just implemented by creating different threshold levels for this Mahalanobis distance based criteria for main effects, 2-factor and 3-factor interactions. Okay. Let me just quickly give you one more example So this was a very interesting example in which I was involved when I was working with the Regenerative Medicine group at Harvard. So they were trying to come up with different possible combinations of chemical modulators, which would help these biotechnologists come up with methods for converting stem cells to insulin generating beta cells. And this would be helpful for treatment of type 1 diabetes. So this is basically the type of experimental unit. Each unit would consist of, so basically each unit is a well which would have about 20,000 stem cells, right? And these stem cells would be treated with a specific type of modulator. And based on that, they would eventually check what percentage of these stem cells are converted to these insulin generating beta cells. So a very simple way of looking at this design is, let us say we have a plate 1 and these are 12 wells, okay? And there are just 2 treatments, 0 and 1. And here is one plate, here is another plate. And I would like to assign these 2 types of treatments represented by 0 and 1 to these 24 experimental units, which are in these 2 plates, right? Physically, how would I do that? So this is obviously not a very good idea, assigning all treatment 1s to one plate and all treatment 0s to the other plate. This is definitely not good, because then there would be a complete confounding with the plates, right? So treatment effect is likely to be confounded with factors affecting plate to plate variation. So we would like to avoid these kind of bad assignments. So we could use the plates as a blocking source. And then within each plate, we could assign 6 to the treatment and 6 to the control, right? Or 6 and 6 to the 2 treatments. Now, obviously, this is not a great assignment. We would like to use a randomization mechanism. So this is what happens in many practical scenarios. So basically, when a biotechnologist collaborates with a statistician, and then she comes up with this kind of an assignment and says that my student came up with this deterministic assignment. Is this okay? The statistician says, this is a terrible assignment. I cannot analyze data because this is not randomized. And clearly, this might have if the treatment effect confounded with the effect of factors which would have an impact on the 2 sides of this block, right? So I would rather use a randomized assignment, right? And then the scientist comes up with a randomized assignment and says, after randomization, my student came up with this assignment that seems to be exactly the same as before, right? So I suppose we should scrap it. But then the statistician says, oh no, that would be cheating, right? Because it is obtained by randomization, it is okay now. Now, this is something which is a very common scenario, because this creates a lot of confusion. Something which apparently was the same without randomized assignment was unacceptable, but now we have exactly the same assignment through randomization, and that seems to be acceptable just because we randomized it, right? So through all this discussion which we have had, I think this paradox can be easily resolved, saying that if we actually define an acceptable randomization a priori, right? So in that case, irrespective of whether this assignment is generated through a randomized mechanism or not, this wouldn't be acceptable, right? So as long as we define an acceptable randomization a priori, everything falls within the same framework, right? So we would just say that there would be a definition of acceptable randomization. In a sense, if we randomize and get this won't be acceptable. So we have to define a criteria by virtue of which the 0s and 1s would be balanced or spread out evenly. So for example, we could use some space filling criteria and say that is our acceptable criteria. And then we would perform the randomization test using that acceptable criteria, right? So once again, this sometimes people just tend to cheat without telling statisticians, because we won't let you change that assignment, right? But then sometimes doctors are also not comfortable with 2 groups. They think they are very similar even after randomized assignment. But if you just define that criteria before you design the experiment, then everything would be logical as long as you analyze it in the framework of randomization test. So I think I would just come up with a couple of quick remarks that so these days it's also pragmatic to combine results from a large number of experimental and observational studies, because people do conduct similar studies with the same inference objective from many experimental and observational from many studies all over the world. So in the age of data science, sometimes there is a requirement of combining these studies to draw sharper inference. So this randomization test actually can be an effective tool when you think of combining similar or dissimilar studies, as long as they all are randomized experiments and they have a known randomized assignment. You could still combine them using mechanism of combining these p-values, and as long as you work under this framework of randomization based analysis. So we have a recent paper where we explore some of these possibilities and come up with some such ideas. So in a nutshell, I think I've been a big fan of randomization tests over the past 6 or 7 years due to these reasons. So first of all, it's very intuitive. It's analyzed as you randomize. So it's very easy to teach. It has a flexibility and broad applicability in the sense it can be adapted with any response, whether it's continuous or binary or ordinal. You can use any test statistic. You can use any probabilistic assignment mechanism beyond standard designs. You can extend it to multiple factors. And you could actually establish theoretically that it is a valid test of the sharp null hypothesis of equal treatment effect for all experimental units. You can invert these tests to obtain confidence intervals, which have frequentist properties. And then you also could extend this to a Bayesian framework where you can actually come up with different kinds of inference on finite populations and larger superpopulations from which these individual observations can be thought of as random samples. So these are a few other references where which are related to some of the work I've done in randomization in the context of randomized experiments. And some of these also pertain to exploring the asymptotics of these procedures. The only difference between the asymptotics of these procedures with standard asymptotics is here we work within a finite population setup. So we have a population of capital N from where we draw a sample of small n, and this population tends to grow. So we have something like a finite population central limit theorem, where I think the population size and a sample size grow simultaneously. And then we have all these nice asymptotic inferential properties of these test statistics. So this is all, and I'm once again, I apologize for the interruptions, and thanks you for this opportunity and giving me some extra time to wrap this presentation up. Thank